Okay, one of the big subjects that we talk about in 8th grade science involves the idea of gravity. And whether it's, in our forces unit or in our unit about space, or actually maybe that's going to be in 8th grade, our unit about space, we talk about something called gravity. And the book will tell you that gravity is the force of attraction between two objects due to their masses, which is all well and good. It's a very good definition. It has a formula that calculates things very accurately, but there are a couple problems with it. But again, this is our definition. This is the one we are happy with, and this is the one that we can base our science on. But I did want to point out a couple things. So let's say we have a beam of light. We have a beam of light traveling through space, and it goes by this massive, massive, massive star. That's a terrible circle, but it goes by this massive, massive star. Well, the gravity of that star can be so massive that the light will actually bend because of the gravity of that star. But the problem is, yeah, the star has all kinds of gravity and it has all kinds of mass, but the light has zero mass. So if something has no mass, it should not be affected by gravity, but light is. Also, we know that if there is, and I know it's white, but this is a black hole. Black hole. If the light gets too close to the black hole, then it gets drawn right into that black hole because the black hole is just an immense source of gravity. But again, light has zero mass. So, there's that problem with this definition. But again, this is a very good definition. This is the one we like, and this is the one that we are going to use. The other part of gravity that people tend to forget, the book does mention it and talk about it, but not only gravity is affected by its masses, but it is also the force of gravity is also affected by the distance between the two objects. Okay, so if the light, I don't know, maybe I should put this in another color. If the light was a little bit further away from that sun or from that star, a little bit away from that black hole, then that light would just continue to travel in a straight line. The gravity would be too far away from the light, and so there would be no effect. All right. So once again, this is the definition that we like, but we have a little bit of a problem with it. Did want to talk about something here, something called the law of universal gravitation, and that is based on the definition that we talked about. And this says, law of universal gravitation says that the force of gravity is equal to the this g constant that you don't even have to worry about. It's just this big, huge number times the mass of the first object multiplied by the mass of the second object over the distance between the two objects squared. And just to give you an example of the importance of distance and not just mass, let's say we have the Earth, and we'll just give the Earth's mass a really easy number. We'll just call it 10. We're not worried about kilograms or, billions of kilograms, whatever it is. And we have another planet that has the exact same mass, okay? And we're going to give it a really easy distance because we need the math to be easy here. We'll make it also 10, but it's 10 squared, right? Because down here, it's distance squared. All right, so if you did the math, 10 times 10 is 100. 10 squared is 100. So that's, I guess we'll write it out, 100 over 100 equals this number that we're getting, we'll just, it's just 1. We're not going to put any units on it, so don't worry about what the 1 is. So if it's the same mass here, and we get this number 1, what would happen if we take the Earth and we compare the gravity the Earth has with another planet that has half its mass? All right, but still the same distance away. So half its mass, you might guess that maybe it's half its gravitational pull. All right, and so we end up getting 10 times 5 is 50 over our 100, and there we go. Yeah, half of the 1. So half of its gravitational number is due to one of the planets being half its mass. Okay, but let's say we have planet Earth, and we'll go back to that first planet where it's the same mass, and instead we spread them apart. We make it twice the distance. So because it's further apart, its gravitational pull should be less. Okay, and since we doubled the distance, then maybe we would guess that it would also reduce by half. All right, but that's not the case. So what we would get, if it's twice the distance, it would be 20 squared instead of 10. So we get 100 over, well, 20 squared is going to be 400. And then we get a gravitational number of 1/4. All right, so this formula shows that, yeah, gravity is based on both mass and distance. And when we do the math, we find out that this distance part has a very large effect on the force of gravity between two objects. Okay, but again, just remember that gravity is due to both the object's mass and the object's distance. Okay. All right. I know it was kind of long, and just to get to this single concept, but I did want to explain some of the problems with what we're taught initially in middle school science.